Hey, statistics, here we go with section 6.5. Charging right through this, chapter 6, situation on sampling distributions. Here we are going to talk about our third sampling distribution, the sample mean. So put a big X bar with a circle on it. That's the third section in a row that we've introduced a new sampling distribution. So here is a review of the two that we already had. Sampling distribution for X by itself, which was just like the count of successes out of a certain amount of people, and a sampling distribution for p hat, which took that X and divided it by n to turn it into a decimal, right, a proportion. So this one was the count of successes, and this one was the proportion of successes. Okay, so we have a center for X, that is n times p. That's from the binomial setting. We have a center for the p hats that just ended up being just plain p. We have a standard deviation formula for X. It went n times p times q. That's from the binomial setting. And we had a standard deviation formula for p hat. It came from the same formula but got changed because of dividing by n. So we had the square root of p times q over n. Now, as far as the shape is concerned, we can say that this is approximately normal under the following circumstance. If n times p is greater than or equal to 10, and n times q is also greater than or equal to 10. Now over here, it's the exact same condition. This is approximately normal if n times p is greater than or equal to 10, and n times q is also greater than or equal to 10. Those are your two, the shape, center, and spread. There aren't really any outliers in this scenario because we're collecting every single possible sample. So shape, center, and spread are what we want to think about while we're describing all of these sampling distributions. Okay, important thing to remember about both of these sampling distributions, the formulas come from the binomial setting from last chapter. That was the don't forget your bins scenario. Okay, both can treat each as a success or failure because we're asking each person, and this is the count of successes and this is the proportion of successes. So we have successes or failures. But because we sample without replacement in general, we can only consider each trial to be independent if the sample size n is less than 10% of the population. That was kind of the important one, and we got to keep our eye on that one. It creates a condition under which we can use the standard deviation formulas. Both have a set number of trials, and that set number of trials is n, and so the probability of success is the same for each individual. So this was the B, I, N, and S, don't forget your bins scenario. So there's your review on a little bit of the last chapter and right up to the last couple of sections. And so now we're ready to move on and talk about the sample means, the X bars, as opposed to X or P hat. Okay, so here we go. In section 6.5 and 6.6, instead of the sampling distribution of X or P hat, we will now focus on the sampling distribution of X bar, an average when I take my sample. The sampling distribution of X bar describes the distribution of every possible X in every possible sample of size n. Same definition, it's just this time it's an X bar in the middle of the sentence. Okay, the mean of the X bar distribution, if I collect a whole bunch of averages from all my samples, I put them together, the mean of all the X bars will be the population mean mu. The standard deviation, well, we don't have the exact formula from the binomial setting because that had a probability of success in it. So what we do is we take the population standard deviation and we divide by the square root of n, because, put this in a little thought bubble over here, the standard deviation for p hat, what happened was we divided by the square root of n because the spread actually gets smaller. And so dividing by the square root of n makes sense to do here as well. The shape of the sampling distribution of X bar, it will definitely be exactly normal, not just normal, it'll be exactly normal if the shape of the population is known to be normal. So you have to be given that in the paragraph for your homework today. But if you don't know that the population shape is normal, we have some stuff to talk about in section 6.6 to verify that condition before we could use a normal CDF to find any probabilities, which is kind of the goal of this chapter of these things. Okay, characteristics of the sampling distribution of X bar. It will be an unbiased estimator, just like the other two, because its mean is mu, the population mean. It's actually centered where it's supposed to be. The standard deviation describes the, well, I'm tired of this, right? The average distance between each sample mean, each X bar, I'm going to put X bar in parentheses there, and the population mean. So the average that they tend to differ when you take different samples from the mean. The sampling distribution is less variable for larger samples, right? And then so I said, well, look, if the standard deviation formula goes over the square root of n, larger n means smaller standard deviation, right? Okay, now that formula for standard deviation, sigma of X bar, requires independent trials. So we're going to follow the same logic that we did for the last two. So if we're sampling without replacement, which is what we usually do, then the sample size cannot be larger than 10% of the population. So at least that condition is the same in order to use the standard deviation formula. But the stuff about the shape and the formula for the spread are a little bit different. All right, let's go to page 3. Here's an example for you. The IQ scores of adults have a normal distribution with a mean of 100 and a standard deviation of 15. We've seen that example quite a few times now. Imagine taking an SRS of 25 people and finding the average of this sample. That would be an X bar. If we did this a whole bunch of times, we could find the mean, mu of X bar, and the standard deviation, sigma of X bar, of the sampling distribution. And it goes like this. The mean of X bar will simply be 100 because that's the mean of the population. And the standard deviation of the sampling distribution of all the averages when I take 25 people at a time would be that 15 over the square root of this 25. That's 15 over 5, that is 3. Interpret the standard deviation. Okay, this is the last time I'm doing it. If this is on the test, we're skipping it, I'm telling you. Interpret the standard deviation as we take more samples. As we take more and more samples, we expect the X bars that we get, or we'll just say the X bars, to be different from mu of X bar equaling 100 by an average of 3 points. 3 IQ points. All right. This part's kind of cool, just to show you how much the standard deviation actually shrinks. I'm going to sketch both normal curves, the one for the population and the one for the sampling distribution. So the population's got a mean of 100, and if I go 15 as a standard deviation, I'll get to 15, 130, and 145. So this is the whole population. So I'm just going to try and draw a big wide normal curve over this that describes my whole population. Now, for the sampling distribution, the standard deviation is only 3. So this will go out, one standard deviation would be 103, and then 106, and then 109. If that's 115, that's 105, that's 110 right there, right? That's 100, 105, 110. We get to 3 standard deviations by the time we're here. So look, it would go 1, 2, and like 3 standard deviations right there. 1, 2, and 3 standard deviations. I don't know if this drawing is making a whole lot of sense to you, but that's as like there's not going to be anything out here. That's it. This normal curve, it's going to be much taller than this one because they both have to have an area of 1, right? It's going to be much taller, and then it's done by the time it gets there. So this area is equal to 1, and this area is equal to 1. It gets really squished together. From the population, find the probability when randomly picking one person that one person's IQ score is 110 or above. So you can see where 110 is. It's about the end of my sampling distribution. But for the population, I would be talking all of that area right there. So it goes like this. The probability that X is greater than or equal to 110 is a normal CDF on my calculator, normal CDF, starts at 110, goes up to 1,000, I'll put in there just an arbitrary big number, and a mean of 100 and a standard deviation of 15. So go to my calculator, and I go second and variables for the distribution menu, go normal CDF from 110 up to 1,000 with a mean of 100 and a standard deviation of 15. So I hit enter that, I get 0.2525. 0.2525. So there's basically just a tiny bit over a 25% chance of picking a random person from the population and having them have a IQ higher than 110. Now for number 5, it's going to be different. Same question, but from the sampling distribution, find the probability when randomly picking 25 people that their average, their X bar, ends up being above 110. So now that we've got this smaller sampling distribution, being above 110 is not going to happen very often. So look, this is the probability that X bar would be greater than or equal to 110. And so that's going to be a normal CDF. And I start at 110, I go up to 1,000. The mean is 100, but this time around, though, the standard deviation is not 15. The standard deviation is the smaller one. It's 3 because I'm taking an average here. So watch, I'm going to hit second and enter, and this just pulls up again. Instead of 15, I'm going to have 3 for my standard deviation, and look at the difference. 4.29, I got e to the negative 4, so that means I got to cross this 4 and put 3 more zeros. This is just 0.000429. 0.000429. Look how much smaller this probability is because this is much wider, and picking one person at a time, you're likely to get somebody way out here. But if you're going to get that person and average them with 24 other people, that's definitely going to pull that number back in. So the averages stay a lot closer to where they should be. Hope that makes sense. Hey, last page. Here we go. We got a book example. So, got to grab a Libro. And on 436, I got my book right here. Let's see what's going on here. The heights of young women follow, so another example that we've done before, follow a normal distribution with a mean of 64.25 and standard deviation 2.5. Calculate the mean and standard deviation of the sampling distribution when we're taking averages of size 15. Interpret the standard deviation. I'm not doing it. I'm skipping it. I'm tired of it. Find the probability that the mean height of 15 women is bigger than 66.5. And then suppose the mean height in a sample of n equals 15 is 66.5. Based on your answer to question 3, what would you conclude about the mean height for all young women at this college? I forgot to point out there's a picture of 2 ugly people. Let's see. We got to find this probability first before we can consider that. So let's, I think I gave you guys room to figure this stuff out here. The mean of X bar, we're told this is a normal distribution. So I'm going to write it up here. It's a normal distribution. The mean was 64.5 and the standard deviation was 2.5. So now I have that handy. That's for the population. Now, the mean of X bar will definitely be the population mean 64.5. The standard deviation of X bar will be that 2.5, but it's going to be divided by the square root of 15 because we're taking a sample size of 15. That's 2.5 over the square root of 15. I put that in my calculator and I get 0.6455. Much smaller than the 2.5. Number 2 said to interpret the standard deviation. I'm just going to say interpret, and I'm just going to skip it because we have done that so many times this chapter I can't take it anymore. Okay, now number 3, it says find the probability that when I take a sample of 15 young women that their X bar, their mean height is 66.5. So this is the probability that X bar is greater than or equal to 66.5 out of that sampling distribution. I have another line there. I'm not really sure why. I don't need it. So I'm going to draw a normal curve. You guys should draw a normal curve every time you do these kind of problems. You should put your mean right in the middle and make sure you know which standard deviation you're using, the 2.5 or the 0.6455. Since this is asking a probability question about the X bar, it's not the 2.5. I'm using the little guy. Okay, so I'm going to go find 66.5. It doesn't have to be accurate. I just want it on the correct side of the mean, and I want to shade in the right direction. Okay, so that is a normal CDF. A normal CDF that starts at 66.5. We'll go up to 1,000 again with a mean of 64.5. I'm writing way bigger than the lines I gave myself. And then remember, the standard deviation isn't the original population one. It's this little one for the sampling distribution, 0.6455. So I'm going to put that into my calculator. Second and variables to go to the normal CDF menu. And I've got 66.5 up to 1,000. 64.5 is the mean. And 0.6455 for the standard deviation for the sampling distribution. And I get another e to the -4, so there's going to be 3 zeros and a 9 and a 7. 0.00097. So apparently, if the average height is 64.5, randomly picking 15 girls and then finding their height to be an average higher than 66.5, even though that's only 2 inches above the mean, that's not very likely. It would hardly ever happen. So question 4 says, let me read it again. Suppose that the mean height in a sample of n equals 15 young women from a local college is actually 66.5. Based on your answer to question 3, what would you conclude about the mean height for all young women at this college? I'm going to say the average at this college is not 64.5 because that happened and it's such a small probability. I'm going to say the girls at this college are likely taller. So their mean, I don't know what it actually is, but I'm going to say it's likely higher than 64.5 inches. If I took a legit random sample of 15 of them, girls, and I got that their average was 66.5, and the probability of that actually happening is this low, well, then the fact that I did get an average that high is really good evidence that this mean isn't true for this college. You guys see how that goes? All right, here's your homework for today. On page 437, you guys are going to do numbers 1, 5, 6, 9, and 17 out of the book. I believe answers are already posted there in Canvas, and we're all set for today. Tomorrow, in section 6.6, we're going to talk about the shape of this. Like, what if we don't know what the population looks like, or if we know the population is like skewed? When could we use a normal CDF anyway? That's what tomorrow's going to be about. All right, have a good day, everybody. Do your homework.